Questions 21 through 25 on the 2016 Grade 10 AMC 10A. Circles with PQR have radii 1, 2, 3, lie on the same line L and tangent to L at P prime, Q prime, and R prime, with Q prime between P prime and R prime. The circle with center Q is externally tangent to each of the other two circles. What is the area of PQR? Here's a diagram that explains everything in the question stem. And now let's start labeling a few things. First, I'll draw a line completely across like that. And then I will draw another line from Q across. And those are, of course, parallel lines. Now let's see what we can label here. The first circle has a radius of 1. So this is 1 and this is 1 where it meets the other circle. Second circle has a radius of 2. So that's 2, that's 2. And the top to bottom length would also be 2. So I can put that in here. And then the next circle, of course, has a radius of 3. So something like that. It won't be perfectly drawn to scale, but pretty decent. So very quickly, we can figure out that since from here to here is 1, this is also 1. And therefore, the distance from here to here will be 2 minus 1, which is 1. In a very similar way, from here to here is 2, so from here to here is 2. And therefore, the distance from here to here will be 3 minus 2, which is also 1. So we can figure out this using Pythagoras, and I'll just call that x. So x squared plus 1 squared is equal to 3 squared. So that means x is equal to 9 minus 1, which is 8. So x will be root 8, which is 2 root 2. We can also figure out the length of this side right here from there to there. I'll call that y. So y squared plus 1 squared is the hypotenuse squared, which is 5 there. So that means 1 would be 24 minus 1, root 24. And that is 2 root 6. All right. So now we've got to figure out the area of a shape that is PQR. So that guy right there. Well, I will do that as follows. First, I'll calculate this area right here, and then I will add to that this full area right here. And then from the sum of those two, I will subtract this area. So that will basically be our strategy. So the first is this shape right here, whatever you want to call it. In terms of our lettering, it's P, Q, P prime, Q prime. The second one is this full shape right there. And in terms of our lettering, that would be Q, R, Q prime, R prime. And then from both of these, that sum, I would have to subtract this shape right here. And that shape will be, let's see here, P, R, R prime, P prime. Okay, well, I think I can do that. And that is, of course, representing PQR. So PQR, that is the shape. All right, so the first one is going to be, it's a 1 times x. Well, x, I can put that in here, 2 root 2. And then y, I can put 2 root 6. So 1 times 2 root 2. And then that triangle on top of it will be 1/2 base times height. So the base is 2 root 2, and the height is 1. Then we move on to this shape, and very similarly, we have initially a rectangle, so 2 root 6 times 2, and then add to that a triangle, and that will be 1/2 base 2 root 6 times 1. And then subtract from that this whole thing. Let's see here, it'll be a rectangle first, like that. So that's just 1 times 2 root 2 plus 2 root 6. And then we'll have to, of course, add the triangle that sits on top of that, like that. So that'd be 1/2 base, which is 2 root 2 plus 2 root 6, times the height of that triangle, which will be, if this is 1, this from there to there will be 2. All right, that's it. Now it's just basically a question of numbers. So this looks like 2 root 2 plus root 2. And then we have a 4 root 6 and plus root 6. And then in the brackets, we will have 2 root 2 plus 2 root 2, so it'll be 4 root 2. And then it'll be 2 root 6 plus 2 root 6, so 4 root 6. So we have 3 root 2 plus 5 root 6 minus 4 root 2 minus 4 root 6. And this becomes 5 root 6 minus, or rather 5 root 6 minus 4 root 6. I can just do that. Root 6. And then 3 root 2 minus 4 root 2 will be minus root 2. And that's it. So the answer to number 21, root 6 minus root 2, and that's D. For some positive integer n, the number 110 times n cubed has 110 positive integer divisors, including 1 in the number 110 times n to the power 3. How many positive integer divisors does the number 81 times n to the fourth have? Well, anytime you have a number, say of the form a to the power of x, b to the power of y, c to the power of z, the number of divisors is going to be x plus 1 times y plus 1 times z plus 1. And any similar variation if you had more letters or more exponents. But that's generally how you do it. So what they're saying is that 110 n cubed has 110 positive divisors. Okay, well first let's break this up into prime factors. So 110 times n cubed is 2 to the power of 1, 5 to the power of 1, and 11 to the power of 1 times n to the power of 3. Now if I use this rule over here, I would get 1 plus 1 times 1 plus 1 times 1 plus 1 times 3 plus 1. And if I do that, 2 times 2 times 2 is 8 times 4, and that is 32. But 32 obviously falls way short of 110. So what's wrong here? Why doesn't this work? Well, the reason it doesn't work straight with the formula is because n, right here, has some of these in it. And therefore, we need to figure that out. So when we look at it, it will probably be something of the form like 2 to the power of something, 5 to the power of something, 11 to the power of something. And therefore, a plus 1 times b plus 1 times c plus 1, that will equal 110, which is the number of positive divisors. All right, so let's work with this now. We have to do a little bit of playing around and see what we get. Well, 110 is an even number, so that means one of these has to be equal to 2 or some multiple of 2. So since I already have 2 here, I'm just going to keep that for now. If it doesn't work out, I can always try something else. So I'm going to keep this the way it is, so therefore my a is 1. So that becomes 1 plus 1. And then I've got this b plus 1 times c plus 1. Okay, and that's 110. So that means b plus 1 times c plus 1 will be 110 divided by 2, which is 55. Okay, we're making some progress here. Well, 55 is 5 times 11, so that means b plus 1 and c plus 1 are 5 and 11. So 1 is 5 and 1 is 11. Let's just say this is my 5 and this is my 11. If that's the case, then means b is 4 and c is 10. Okay, so let's go back here and plug those in and see what we get. 2 to the power of a, I had selected a to be 1, if you recall. So I'll put that there. B to the power, well, 5 to the power of b, I've got b as 4. 11 to the power of c is 10. All right, and that would make this work. It would be the number of divisors would basically be 2 times 5 times 11, and that is indeed 110. Okay, great. So I figured out what is my original number. My original number, 110n to the power of 3, is 2 to the power of 1, 5 to the power of 4, 11 to the power of 10. Okay, so that means that if I were to try to figure out n cubed, I need to divide both sides by 110. So that would mean 2 to the power of 1, 5 to the power of 4, 11 to the power of 10. 110 was 2 times 5 times 11. So n to the power of 3 is 5 to the power of 3, 11 to the power of 9. There we go. And therefore, if I take the cube root of both sides, n is 5 to the power of 1, 11 to the power of 3. Now they want me to figure out what are the number of divisors of 81 times n to the power of 4. 81 times n to the power of 4, well, n is this guy, so it'll be 5 to the power of 1 times 11 to the power of 3, all to the power of 4. So this looks like 3 to the power of 4, 81, 5 to the power of 4, and 11 to the power of 12. Okay, so now I use that standard formula to figure out the number of divisors. And when I do, I get the following. It'll be 4 plus 1 times 4 plus 1 times 12 plus 1. And that looks like 5 times 5 times 13, 25 times 13, which is equal to 325. And that is the answer to this question. Number 22 is D. A binary operation, diamond, has the properties that A diamond bracket B diamond C is equal to A diamond B times C, and that A diamond A is equal to 1 for all non-zero real numbers A, B, C. Here the dot represents the usual multiplication operation. The solution to the equation 2016 diamond 6 diamond X is equal to 100 can be written as P over Q, where P and Q are relatively prime positive integers. What is P plus Q? We have to do a little bit of experimentation here, and it all starts with this guy right here. A diamond 1. Well, according to this definition, it would be as follows. Inserting this for 1. So I've got A, I've got this diamond, and this 1 right here is equal to A diamond A. So I can put that there in brackets, A diamond A. So it all starts from here. I think that's the hardest part of the question, is knowing where to start. The rest is pretty straightforward. Okay, now I've got this. Now I go directly to the definition right here to figure out what is this. And that would be A diamond A, and then multiplied by A, like that. Well, A diamond A right here, they have told me in the question is equal to 1. So put that here, times by A. 1 times A is just A. So I conclude that A diamond 1 is equal to A. Well, previously we had substituted for 1 A diamond A, which is right there. But I would like to introduce B into the equation, since we have a B here, and I'll do that for this one. A diamond 1, but 1 can also be B diamond B, because it's true for all non-zero numbers A, B, and C. So this 1 is B diamond B. It can be written like that. Now, this part, we go right back to the definition, and it would be A diamond B times B, and that's equal to A. And then A diamond B, you put the B on the other side, so it'd be A over B, like that. And there we go. We just figured out what is that binary operation. So I think that is relatively challenging, considering we have to know that we must start with A diamond 1 to figure all this out. All right, so now that we have the actual operation, we can proceed with this guy right here. That one is 2016 diamond 6 diamond X, and that is equal to 100. 2016 diamond, well, 6 diamond X, according to this binary operation, would be just 6 over X, like that. And that's 100. And then now this guy, according to that definition, would be 2016 over 6 over X is equal to 100. Cross multiply, and you get 2016 is equal to 600 over X, and therefore X is equal to 600 over 2016. There we go. We've just figured out the solution. But is it in the form P over Q, where P and Q are relatively prime integers? Well, not really. It's got to be in lowest terms. So when you reduce this to lowest terms, it eventually becomes 25 over 84. Now it's in the form P over Q, where P and Q are relatively prime positive integers. And now they want you to find P plus Q, so it would be just 25 plus 84, and that is equal to 109. And therefore, number 23, the answer is A. A quadrilateral is inscribed in a circle of radius 200 times root 2. 3 of the sides of this quadrilateral have length 200. What is the length of the fourth side? Here is a diagram. Here is A, B, C, D. And then we are given a few of these. This is 200, this is 200, and this is 200. And in particular, we also are given the radius. Now, to put the radius on the diagram, I've got to draw the center. So probably here, and then let's just draw 2 radii, one to there and one to there. And now those red lines that I just drew have a value, 200 root 2. So I'll just put that up here instead of making the diagram messy. So those radii that are represented by the red line, and this is C for center. And then this point where it crosses, I'll write E and then F, like that. And just for the sake of completion, I will draw a couple more lines from A to C and from C to D. And I think that should be sufficient. Now, what we have to do in this question first is a whole bunch of angle chasing. The angle chasing is basically labeling angles, right? Like this is a theta, so that's theta minus 90 or whatever, right? And what that angle chasing will eventually make us conclude is that there's a bunch of similar triangles here. Okay, so let's begin. And I'm not going to walk you through it because, you guys know how to do angles in triangles. The sum is 180, and, you don't need me to walk you through it. Well, this triangle right here is isosceles since those are radii. So that means if this is theta, this is theta. And then this guy right in here would be 180 minus 2 theta. Okay? So that's the beginning of it. And then very similarly, this is also an isosceles triangle. So this is theta and this is theta. All right? And then the next thing, same kind of story here. This guy in here, right here, would be 180 minus theta, like that. And then similarly, this and this are also theta because basically it's the same triangle. This is the same as the other one, this guy. they have the same side lengths, two radii and 200. So this is theta, and this whole thing is theta. And therefore, this guy in here would be 180 minus 2 theta. Like that. And then you can figure out this angle in here by subtracting from 180 this and this. And when you do, you get 3 theta minus 180. And then you can figure out this angle by subtracting from theta 3 theta minus 180. And when you do, you get 180 minus 2 theta. This guy in here. 180 minus 2 theta. And then finally, this angle you can get since we know the other two. And when you do, you find that's theta. So I'm sure you guys are very well versed in angle chasing. But what does in this question is allow us to conclude that triangle ABE is similar to triangle CEF. And in particular, ABE is this one right here. It has 180 minus 2 theta, theta, and theta as the angles. And triangles CEF. CEF is also 180 minus 2 theta and theta. So that is basically what I wanted to, illustrate. Okay, since those two triangles are equal, or they're similar, or whatever you want to call them, they're not equal, they're similar. The ratio of the sides will be equal. So AB over BE will be equal to EC over EF, and that is equal to CB over BC. All right, let's see what we know. AB is 200. BE I don't know yet. EC I also don't know yet. And EF I also don't know yet. CB, that's the radii, and that's 200 root 2. And BC is 200. Okay, great. So I can systematically now calculate each of these. This equals that, so I can figure out what is BE. That would be, let's see here, 200 over BE is equal to this, which is just root 2. So that means that BE would be 200 over root 2. And when you multiply top and bottom by root 2, you get 100 root 2 for BE. Okay. EC, I think I can figure out from this now that here's EC right here, from here to here. And since we know BE, we can figure out EC. EC is basically BC minus BE. And BC is just the radii, so that's what, 200 root 2. And then BE we just figured out was 100 root 2. So that means EC is 100 root 2. Okay, and then finally we can figure out EF using this equation right here. We've got EC over EF is equal to root 2. EC is 100 root 2 as root 2 EF. So that means EF is equal to 100. All right, we're done. Final step. The question asked us to figure out the length of the fourth side of that quadrilateral, and that is AD. Well, AD looks like it's equal to AE plus EF plus FD all the way across. AE is from here to here, which is the same as from here to here, since that was isosceles, since these two angles were the same. So that means AE is the same as AB, which is 200. EF we actually got right there, so that's 100. And then FD, because of the symmetry of this diagram, you'll be able to show that FD is the same as DC. So that's 200. And therefore, adding it all up, we get AD is equal to 500. And 500 for number 24 is choice E. How many ordered triples xyz of positive integers satisfy LCM xy is 72, LCM xz is 600, and LCM of yz is 900? We are given a few clues. Lowest common multiple or least common multiple, whichever way you'd like to say it, is 72. So I'm going to break this up into its prime factors. I think that will be most helpful for us. 72 is what? 2 to the power of 3 times 3 squared. All right, moving in the same way, the next one is xz, and that's 600. So that means LCM of xz is the prime factor of 600 would be 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 2. And then the LCM of the next one is yz, and that's 900. So breaking that up into prime factors, we would get 2 to the power of 2, 3 to the power of 2, and 5 to the power of 2. Okay. So what I'm going to do is use some triangles to kind of illustrate all this. I hope it helps. So if you have x, y, and z, let's see what we get. Well, x and y have a least common multiple of 2 to the power of 3, 3 to the power of 2. And then x and z, 2 to the power of 3, 3 to the power of 1, and 5 to the power of 2. And y and z are 2 to the power of 2, 3 to the power of 2, and 5 to the power of 2 with regard to their least common multiples. All right, so now what we want to do is take a look at this one prime number at a time. So first, let's just start off with the 2's. And we'll then talk about 3's, and then at the end we'll talk about the 5's. So let's just look at the 2's. Well, it's 2 to the power of 3 here, 2 to the power of 3 here, and 2 to the power of 2 here. 2 to the power of 3, 2 to the power of 3, 2 to the power of 2. Okay, so that obviously means that x has a 2 to the power of 3 as part of its factors. It might be entirely equal to 2 to the power of 3, or it might have 2 to the power of 3 as part of its factorization. But regardless, it definitely has 2 to the power of 3. So now I've got to figure out what is y and z. Well, they have a LCM of 2 to the power of 2. So we've got a few choices here. It could be 2 to the power of 0 for y and 2 to the power of 2 for z. Or it could be 2 to the power of 1 and 2 to the power of 2. Or it could be 2 to the power of 2 and 2 to the power of 2, 2 to the power of 2, 2 to the power of 1, or 2 to the power of 2 and 2 to the power of 0. Any of these would satisfy y and z having an LCM of 2 to the power of 2. And as you can see, there's 5 such ways of arranging y and z, or creating y and z. All right, so now that's pretty good. Let's move on to the next one. The next one will be talking about 3's. So here's x, here's y, and here's z. And now I've got to put 3 to the power of 2, 3 to the power of 1, and 3 to the power of 2, like that. So 3 to the power of 2, 3 to the power of 2, and 3 to the power of 1. So obviously y is equal to 3 to the power of 2, meaning 3 to the power of 2 is part of y. That's pretty obvious. Now I've got to figure out x and y. Well, x and y, a few choices, right? We can have either 3 to the power of 1 for x, and z could be 3 to the power of 1 also. Or you can have 3 to the power of 0 for x, and 3 to the power of 1. Or you can have 3 to the power of 1 here, and 3 to the power of 0 here. I think those are the ones that would be the only ones. Yeah. So that means this combined with this gives me 3 possibilities. 3 arrangements for x and y. Either this guy with this guy with this guy, or the 3 to the power of 1 with 3 to the power of 0. So that's 3. Okay, so I think I'm getting close here. One final triangle, of course, and that's got to look at the 5s. So let's look at the 5s now. So here we go. X, Y, and Z. And let's see if I refresh my memory here. There was no 5 here, 5 to the 2 and 5 to the 2. Okay, so that means 5 to the power of 0, 5 to the power of 2, and 5 to the power of 2. So that means Z must be my 5 to the power of 2. And then the combinations for X and Y, X can be, well, there's only one choice, 5 to the power of 0, and Y 5 to the power of 0 for X and Y, these two. That's it. So that means I've only got one possible way of setting up X and Y with regard to powers of 5. Okay, so I'm ready to figure out the total number of cases. 5 number of cases for the 2's, multiply that by 3 cases for the powers of 3, and multiply that by the 1 case for powers of 5. And 5 times 3 times 1, of course, is 15. And that is the total number of ordered triples, X, Y, Z, that satisfy the conditions of the question. So number 25, the answer is A.